Greetings, Earthlings. Today, we're going to look at the stupid computer running machine language. I've written the taken an initial pass at the microcode for the instruction set and implemented that. And so we're going to go ahead and try a few little simple tests and see if that's actually functioning as intended. So we'll go ahead and plug it in here. Now, one thing I have done is implemented a power on reset. You saw the lights flash. Whoa, that was doing, power on reset, a power on self-test. That was doing a quick memory test, clearing the registers. I'll probably expand on that as time goes on. But does that only on power on? If I do a reset, you'll notice the lights don't flash. Now, how do you tell a power on reset from a switch reset? Because to the computer, it just sees the reset line pulled low. Well, I played a little trick there. You'll notice that the stop switch and reset switch are on the same physical switch, okay? So it is impossible to press stop when you press reset. And so I used that to my advantage. What I did is in the debounce circuitry, I gave the stop switch a longer time constant so that when you power on, the reset will come off of the reset condition before the stop switch comes off of the reset condition. So it tests at the very beginning of the microcode whether the stop switch appears to be pressed. And if so, it says, oh, this must be a power on reset. I can run the power on self-test. Otherwise, it doesn't. So let's run our first test. I have a little 4-instruction test program here. Clears the accumulator, increments it, and skip if 0, branches back, so it'll loop there between those two instructions, halts when it's done. Okay, so we're at location 0, memory address 0. I want an FF1. There's an F, there's an F, and there's a 1. I deposit that into location 0. Location 1 gets FF7, 7. Deposit next. Location 2 gets a 101. Hex, well, I'm in hex right now. 101. And location 3 gets FFF. Okay? That's the program. I can go back and verify, examine location 0. That is FF1. Examine next. Location 1 has FF7. Examine next has a 101. And examine next, FFF. Okay, good. So, set the switches to 0 and press start. Oh, it's done. Okay, that was really exciting, wasn't it? Let's try this again. And notice the PC here is at 3, which is the halt instruction. And there is the halt instruction there in memdata. If I reset, that's going to clear the PC. So I can step through this, okay, which may be a little more interesting. There's location 1, there's location 2. The accumulator has now 1 in it, okay? Goes to location 3. Oh, actually, I'm sorry. It branches back to location 1, increments the accumulator, back to location 1, increment, and so on. Okay? So you can see that it actually was running the code. It's just that when you execute it, it just runs very quickly, which is a good thing with computers. Okay, next test. Well, what does everybody do? What's the first program you always write? It's hello world. And I can do that, and that is 9 instructions, but I wanted to, and plus the string to output. But I want to talk about the indirect registers, because we haven't seen those in operation yet, and there is a problem with the implementation of the indirect registers. I'm using, as you may recall, if you've watched the earlier videos, I'm using 74F670s because I found some. And I said, these would be neat to use. Let me see what I can do with them. So that's a it's a register file for 4 registers. However, it turns out they're implemented as transparent latches, not as edge-triggered D flip-flops, for instance. So that if you read and write to the same instruction and you have a feedback loop, so say you want to increment an indirect register, you would say read from that indirect register, pass it through the ALU, increment it, and pass it back in to the same register address. Well, that just passes right through and it loops around again and again and again and again. And so it increments by much more than one. So I've worked around that in this code. I am using the indirect register to load the string, but I'm incrementing it sort of manually by actually moving that indirect register value to the accumulator, incrementing it, and then moving it back, which is really horrible. But that's not, okay, 2, 0. That's not a fatal flaw. It just means that certain instructions that I thought I had, I'm not going to have, and I'll have to deal with it, you know. It's not, to fix it, I'll say to fix it would be difficult. One thing I could do is yank those 670s out. But that board is full that it's on. So if I try to use other registers in there, for instance, 174s, which I use for all the other registers, I wouldn't have enough space. If I tried to, let's see, F, E, 2, F, 0, 2, F, yeah, so anyway, it's simply not, I don't have the instruction set that I thought I would, which is a shame. But that's life in the fast lane. Okay. Now, okay, so that was, okay, going through the code. Load accumulator with the string pointer, move the accumulator to the indirect register, move the address that the indirect register points to the accumulator, check if it's 0, this is a null terminated string. If it's 0, it'll halt, otherwise it prints the character, moves the indirect register back to the accumulator, increments it, and branches back up to location 1 here, which moves the accumulator into the indirect register, and just keeps going until it hits the null. So location 20 has the address of the string, and I'm putting the string at 30 hex. This is all hex. Okay. And of course now I'm going to switch from hex to octal because ASCII characters are easier to deal with in octal. So at location 30, carriage return, line feed, 1, 1, 1, 0, 1, 0, 5, 1, 1, 4, 1, 1, 4, 1, 1, 7, 0, 4, 0, 1, 2, 7, 1, 1, 7, 1, 2, 2, 1, 1, 4, 1, 0, 4, 0, 4, 1, 0, 1, 5, 0, 1, 2, and null. Okay, so this starts at location 0. This code, by the way, of course, the code itself is relocatable because the only branch is a relative branch, and the fixed address is the pointer to the data and where the data sits. But I could have put this code anywhere in memory. I decided to put it at 0 and start. And nothing happened. Let me check the code. It's 2, 2, 2, 0. F1, 8. Let's try F1, 4 instead of F1, 8. Okay. F0, 3. FFC. FFF. FE2. F0, 2. Oh, what did I do? I'm sorry. F. 5. That goes in location 7. Okay. Examine next. Okay. 1, 0, 7. Okay. Let's try this again. Reset. That puts the PC back to 0 and start. There we go. And I hope you can see that. Tear that off. Hello world. I can run it. I can just keep running it. Okay, so there you go. Hello world. That's it for now. One thing I haven't looked at yet in any great detail is the load operation. What I intend that to do is load a program into memory over the serial line, and I'll have to define how that works. I also need to look at, well, I said what I cannot do with the indirect registers. Maybe there's some other things that I can do to make the code a little simpler. For instance, right now, it's 2 instructions: move the indirect register to the accumulator and increment the accumulator. I may be able to say move the incremented value of the register to the accumulator and save an instruction here. You'll still have to move it out and move it back. But that would save the increment, or the decrement, by the way, instruction. So we'll see. It's all to be determined. I have to verify that all the instructions that I have defined work. I'll look at all of them. You know what? I think I need another assembler.